okay?
Yes.
Because we're restarting. Okay, welcome everyone. I'm Jeff, call it Dr. Jeff Kuhn, and I'm here with Kevin Surfer Legend Lewis, and we're here on Life on Planets Conversations. We're here to explore the question, we're not special, and that's probably a good thing. And what we do every week is Kevin and I will talk about the latest news, cosmic news, news of importance in understanding our place in the universe. And today, Kevin, what are we going to talk about?
We are talking about the Breakthrough Starshot group. And Jeff, why don't, in case people don't know what Breakthrough Starshot is, maybe if you could give a little introduction to what it is.
Absolutely. So Breakthrough Starshot is a research program to prove that it's possible to send interstellar probes on timescales of a human lifetime, which is a really exciting possibility. It means that we could send information and retrieve information from the nearest star system, which is a few light years away, Alpha Centauri, in a matter of, say, 20 years. So Breakthrough Starshot is a program to do just that, with little probes that are just a couple of grams in size, maybe a gram, that would be propelled at 20% of the speed of light. And they would, in a matter of something like 20 years, be in location, speeding by Proxima b or Alpha Centauri, and then beaming back to us information about the conditions on the planets that we believe exist around those stars. So it's a program funded by a wealthy internet investor, I guess is how we would call Yuri Milner. He's provided incentive to a group of scientists and engineers and futurists to lay out a plan for creating a program that would get us there in a matter of a few decades. He's passionate. The group that's doing it is passionate, and they've just started a program to try and understand it. Now, I'm not a spokesperson for that program. I'm speaking as an individual passionately interested in the success of that program. The official spokesperson is Yuri Milner himself and Dr. Pete Warden, who lead that effort. So let me get that disclaimer out in front.
Perfect. Thank you for that.
Okay.
So a lot of the questions I have, they're kind of just going to get into the nitty-gritty of the reality of this, or how much progress we need to make in each one of the components. But before that, what's your involvement in the Breakthrough group?
So what Milner has done is to put together a group of scientists that are supposed to provide some kind of advice on how to go forward with technology that just barely exists right now to do this. And I'm on his panel of advisors. My expertise is telescopes and physics in general, and I guess that's why I'm there. The panel is a big group of people that includes some folks that have been thinking about interstellar travel for years and years and years, and some technical people that, for example, know a lot about lasers or know a lot about optics. So it's this broad mix of folks that share really one common element, which is they're all really passionate about this problem, and they think that it will change our understanding of ourselves and the universe, and that's what it's about, really, perspective. We're trying to figure out whether or not we're really special. Is there life on the nearest planets? When you wake up in the morning and you think, gosh, I'm special, this is a great world, how would you think differently if you woke up and you saw on the news a picture of another planet that didn't look a whole lot different than the Earth, and it's only about 4 light years away from us, right in our neighborhood in cosmic terms? You might think, well, maybe life isn't so fragile, and maybe there is hope for us to survive global warming, mass conflict in the Middle East, and all the other political and social upheaval that we worry about in our nightmares at night. Wake up in the morning and seeing this newscast, I think would make a huge difference in the way we see life here. So I think it's existential. It's really important that we do this.
Yeah, I mean, you would hope so. You would hope that there would be less conflict, especially in the Middle East or all over the world, if we found another planet, especially another planet with life on it. I mean, we obviously found other planets, but another planet with life on it.
Well, yeah, I think, the idea there's this kind of the scientific community and people in general have thought, oh, we're special. Every one of us is terribly special. Well, that's what your mother taught you when you were a young babe. You lived in a universe that was your very own universe until you emerged out into this bigger one. And the process of getting older is this process of learning just how unspecial we are. Well, maybe the next step is, in fact, the life that we know in this universe that we call just the Earth is a tiny, tiny piece of everything else that exists around us. I think that part of the reason for science and exploration is just that fact, to show how unspecial we are and how we're part of some sort of larger ecology. Anyway, I digress. The truth is
Sure.
that this is an exciting and very, very optimistic research project that will go on for years. And we're lucky to have somebody, a vision like Milner, who's willing to put up a whole bunch of money to try and make it happen.
And what are these meetings like? Can you tell me anything about the actual meetings? Like, I don't know, in my head, I just probably envision something that's not even close to reality, but
So I'm sworn to secrecy. I can't, no, it's a bunch of very passionate people, mostly arguing about, well, is there a better way? Okay, all right. So first off, it's a really hard problem, right? Nobody has ever accelerated any macroscopic object to 20% of the speed of light.
Or even remotely close.
It turns out one of the fastest objects in the universe was a manhole cover that was propelled. We think it beat the escape velocity of the Earth, and it was an underground explosion.
No way.
Yeah. The data is interesting. It was just one frame and a very, very high-speed camera, and so we just have a limit on its velocity. But apparently, that's accidentally the fastest object mankind has created that's macroscopic in size. So, all right. So the basic picture
that's
here
totally
is,
true. You're not just
no,
joking.
You can look it up. Look up the fastest object on the Earth. As I talk, you can go to the web and you can find it. It's absolutely true. So our problem is that we have to propel a 1 gram nanocraft, which is about like this. So Pete Klupar and a group at Breakthrough have a group of scientists who've already developed some of the microcircuitry that you would put on this. It's literally about that big in size. And it weighs a gram, and it has on it a camera, and it has what we think of as photon thrusters that give, with a little bit of power, enough maneuverability once it gets started. The secret is to get it started, and to get it started, we need a sail, which is, say, 2 to 4 meters across, highly, highly reflective. It's got to be like 99.9999% reflective in order not to burn up. And then we have to have a huge laser system, 100 gigawatts of power, that is focused on the sail, which is released in the environment of the Earth. Focus the energy on the sail, and for about 2 minutes, it gets this 100 gigawatts of power, and it gets accelerated at something close to 60,000 Gs from a relatively small velocity to 20% of the speed of light, and then it's off. And maybe it's autonomous. Maybe we aim it in the right direction and it passes through Alpha Centauri. Maybe it more than likely has an onboard sensor, so it looks in the direction of Alpha Centauri and knows how to gently adjust its travel direction from these other photon thrusters. And then when it gets there, a long way off, we get a few images, and we use that same reflective dish to transmit a signal back to the Earth. All right, so that sounds easy enough, right?
Yeah.
Well, okay, yeah. So then you start thinking about about the reality of it, and the numbers are really daunting, and that's what this group is struggling with. How do you phase all the lasers? How do you make the optical system? How do you make the reflector material reflective enough so it's not burned up? Can you really expect this to be autonomous and not to communicate with it until it sends back a signal? All kinds of stuff like that.
The material sciences, I mean, I'm sure all of them are equally as difficult, but that seems like it's the hardest. Like that, creating it so reflective that it doesn't just completely vaporize when you shoot shoot the lasers at it.
Yeah, you'd think
that
so. That sounds hard, doesn't it? But it's not completely hard, and there are theoretical solutions that are already appealing. One of them is you can go look this up. It's called Anderson localization, and it's a really clever way of building reflective, one-dimensional Anderson localization. Those are buzzwords, and we could get into it, but it's not worth it here. Search it on the web, and there are these ideas for making mirrors out of multi-layers of random. Think of making a mirror out of a bunch of, well, you're too young to know what a transparency is in an overhead projector, but if you take a whole bunch of...
I had those in grade school. I know.
Great. Okay. Well, I had them through my formative years. If you took a stack of 100 of those and each had a different thickness, the resulting surface would be highly reflective over a range of wavelengths. And of course, that, by the way, is one of the problems. That as this nanocraft is accelerating away at 20% of the speed of light, as it gets faster and faster, the wavelength of the laser beam at the spacecraft is getting longer and longer. So it not only has to be highly reflective, but it has to be highly reflective over a range of various wavelengths.
Right, and then the lasers have to be. I mean, you're altering the actual lasers too. It's not just one.
Mm-hmm. So on the committee are some advisors, Nobel Prize winners, that have basically weighed in with their prediction of technology in the next decade, and their feeling is, now we're not going to be able to chirp the frequency of the laser. Right? If we could change the frequency of the laser so we could increase the frequency on the ground, as the spacecraft accelerates away, you might imagine that at the spacecraft, the color or the wavelength of the laser would stay the same, but that's too hard. It's probably much easier to make the spacecraft reflective, or the stellar sail reflective at over a range of wavelengths. And this idea that I just mentioned, Anderson localization, is a really, really clever approach to making mirrors that nobody's made work yet in reality. But that's what this is about. This is about pushing the envelope and taking ideas that don't violate the laws of physics. So Milner's vision here is that come up with a solution which is forward-thinking, is possible because it doesn't violate the laws of physics that we know, and make a plan. And if you have to do some basic research along the way, that's great. I mean, for example, right, the people that have talked about interstellar travel with strange kind of, warp drives, things like that. Well, maybe that works, but here's the problem. We have to change the laws of physics. The main laws, we have to make negative energy, negative mass. And then if you make negative energy and negative mass, then you can construct solutions that do this sort of warp-like things, excuse me. And right, those are off the table right now because it's new. It's completely new physics. And maybe in 100 years, we'll know more, and we'll know more than we know or could know. But that's not what this is about. The rules are use the laws of physics that we know to make something that gets there. And it's, that's admirable. There's no magic here. We're not using any magic. It's got to be real life.
Sure. Yes. I would hope that no wizardry is involved.
No. In fact, my mantra in all of this is that yes, we live in an OUIP, an optimistic universe of infinite possibility, and that's we'll see. This group has just got started. I think publicly, anybody who's interested should go to the website and public inquiry should go to Pete Worden and Yuri Milner, but as a scientist, I can say there's a fair number of excited people that think that we could actually make this happen. And not next year, not 10 years from now, but within 20 years.
Right. Okay. So I've got a question from online. It is from Connor, and he's asking about nanocraft.
Thank you, Connor, by the way.
Yes, Connor's great. Something that small actually be able to send back data and
yeah. Okay, all right, Connor, let's take that question apart. It's not actually going to be that small because it has this very lightweight sail, and the sail has to be we figure between 2 and 4 meters in size. So that sail either folds up and then redeploys once it gets there, but it provides a basic optical surface to produce a signal that gets back to the Earth. Now, it's not easy. The signal to detect the information that comes from that think of it as an umbrella that reopens, and it's an umbrella which is big. You can't see my arms, but it's big. To see that requires, there you go. Although I that scale is a little wonky, right? Because that's only 2 meters across, that yellow thing.
Okay.
But from 2 meters across, if we had a telescope that was, say, about 1 kilometer across, we could collect enough information to make real images. And they wouldn't be real high resolution images, but they'd be images that are good enough to make sense of what's on the planet. So if you had oceans and continents, you'd surely see them with this sail and with the imaging. So your question is good. It's not actually this much which is broadcasting, but it's a big sail that does it.
Okay, so you have these little nanocrafts that are actually attached to the cell. I didn't totally follow that.
Well, there's a lot of stuff to work out there. So the nanocraft have to be attached to the sail because it's the sail that collects the energy from the 100 gigawatts of laser power that propels it.
Right.
And then, and so you either shield the nanocraft so it's it's in the lee side of the sail, or it's in the downstream side of the sail, but it has to physically connect it in order to be propelled, and also to be able to wire the information from the camera lives on the nanocraft. But who knows? It's possible that we could design the sail to be integrally part of the nanocraft. These are early days, and the question you're getting at maybe is that the mass distribution on the sail to be stable. I mean, there are lots of things here, right, that are real hard problems. One of them is this sail, which is being accelerated at 60,000 Gs. Well, that
within 2 minutes, right? Isn't that the idea? It's like
the acceleration is instantaneous, almost. I mean, the first time that beam hits that big reflector, it starts moving with that acceleration. And you say, wow, how can anything survive that acceleration? But this is the magic. Acceleration is so. At our last meeting, somebody pointed out that the jaws of a particular ant, and this has been measured, the jaws of a particular ant accelerate at about 50,000 Gs when this is a biological system. When they, I guess they can actually explode their jaws and move their body, or they clamp them closed. And
I think I've seen that on like some. They jump in the air.
Yeah. So the point is that if the mass is low enough, the force associated with 60,000 Gs is remember, force is equal to mass times acceleration, right? So if the mass is small, even though the acceleration is high, the force is a manageable thing, and that of course is the point in all of this. But anyway, the answer to the question is that the nanocraft has to be attached to the sail somehow, or be part of the sail.
Okay. Gotcha.
And that works. I mean, we can make it work. We think we can make it. It doesn't violate any laws of physics. And I mean, even I found it entirely, a bunch of the physicists on the committee said, well, this is a little dubious, 60,000, how does the sail not tear itself apart? Well, okay, so there's work to be done there, but the truth is that there are even biological systems that live at that kind of acceleration. So
Sure.
So have hope.
What's the name of this ant, Jeff? So I can.
Yeah, well, okay, we'll post it. We'll post it. The notes to the show. Okay.
All right. Perfect. Okay. Here's another question. So,
by the way, I'm not sure it's an
actually,
ant. It might have been a bug, a different bug,
okay,
a beetle, or something.
Maybe we can just put a bunch of ants on the nanocraft.
Well, we have to do some biological.
And coat there.
They have to be engineered to be able to. Yeah, maybe compound eyes. A compound eye structure might work.
Right. So here's a question. So pointing the camera at the planet, that seems pretty difficult. Is there a way to have some type of 360 camera on the nanocraft, or is it?
I think what we want is we want a light field. So don't think of it as a regular CCD. But think of it as some, by the time this thing goes, we're going to have miniaturized cameras that measure directly not just the number of photons that strike a pixel, but their angular distribution. So we can reconstruct the light field and make images without having to worry about focus or a lot of the pointing details. So I think so look up light field imaging. They sort of exist now, and it's the idea that you can form an image with a detector that can see not just the number of photons that hit a pixel, but the direction that they come from. And if you have that information, then you can make an image after the fact, with good resolution and optimize it for things related to pointing. So there's another problem here, right? Which is this: we don't know how to stop the nanocraft. We can't stop it when it gets there. It has to whiz by, and we've got a couple of minutes as it goes. But don't fear, right? Once we have all of this infrastructure built, we can send these things off like potato chips. I mean, we're gonna be able to send one out as often as we can charge up this massive laser system. I mean, okay, to set the scale here, right? The laser is 100 gigawatts. That's sort of 10% of the power budget of the entire United States. So we have to have a way of. We're not going to be running this thing continuously. We're going to charge up some sort of a battery bank or flywheels or some energy storage mechanism. Fire the laser and
thorium, right?
Thorium, yeah, right. Thorium.
I don't know. Have you have you seen that?
I don't know that one.
There's a group going around that's all about.
Reactors, because they're safe.
Yeah. And I don't know. I guess there's plenty of thorium laying around in mines.
Yeah, well, there's plenty of sunlight too, right? So to get actually 100 gigawatts of solar power wouldn't really be, for 2 minutes wouldn't be really hard. You could, if we built this in a sunny place, a big area, hundreds of acres of solar cells could collect enough power if we could store it to run this thing. So, I'm not so worried about that. I think
me neither.
Harder things are related to the nanocraft and so forth.
Sure. All right. Yeah, I'm with you on that. What about financing? So he's pledged $100 million, which that's definitely a chunk of money. But to me, it seems like at some point there needs to be some type of momentum carrying this forward. Like, when we went to the moon, we were worried about the Russians going there first, and we upped everyone's taxes, and there was this like huge drive, and we did it in a fairly short amount of time.
That was sort of the politics of fear, right? I don't know. Maybe we could start a rumor that the Proxima B Centaurians, now that we've discovered them, they're worried and they're mounting an offensive against their nearest neighbor. And so we better get with it and find out what they're doing. So that's an idea. We get some kind of momentum associated with the fear of interplanet. No, I know we can't do that. This is science. This is our own existence that should keep us motivated. Is there life on the universe, or are we the only speck, only planet that where evolution ever took a foothold, and where bipedal creatures like us developed? That's the question. That's fundamental. It's absolutely fundamental. Because if we are, then if we're the only thing around, God, we really, it's going to be sad when it doesn't, when we're not here. On the other hand, if we find life, then there's optimism, and we know that it's not rare and fragile.
Right, and then I mean, on all kinds of rabbit holes. If we are out there, like maybe we live in a simulation. I know you don't really like that theory, but
well, I mean, somebody has to write this. No, that just pushes the problem of life and where it comes from and what it's for further back, right? Somebody had to write the simulation. I happen to believe that, and we could get into this another time, but the evolutionary history of life and the development of living complexity takes longer than the lifetime of the Earth. I'm just convinced of that, and there's some data to support some of those ideas, which means then that life really is a cosmic thing, not just a local accident. But that's another story.
Well, hang on though. I don't want to leave that alone. So, are you at what aspect? Like you're talking about the very early stages from like.
There are so many mysteries in evolution, so many jumps that are just so hard to understand. Okay, well, I'll leave you.
Like prokaryotic to eukaryotic. I'm not pronouncing that right at all, I know, but.
Sure, the development of complexity in biology is something which has been. Some people would say it's kind of like a more, right? The development of complexity in our technology. Think about integrated circuits. It doubles every 2 or 3 years, right? That's Moore's law. And,
yeah, sure.
And the people that believe in a singularity, which I think is a really interesting idea, would say that, well, we can extrapolate that complexity up to a point where you reach, say, the human brain, right? And what happens then? Okay, so development of complexity, and the idea there is that the more complex the system is, the more complex is its evolutionary development, and that produces this exponential kind of growth, a doubling of time. Well, okay, so why should biology be any different? We can measure the complexity of any organism, and I believe this by counting the number of functional base pairs in the DNA. Now, there's the key word, functional. DNA has a lot of repetitions and false starts and things in it that according to my molecular biologist friends, don't have useful information. But if you were to take, and suppose you could do it, measure the number of functional base pairs, then I think you would find that from the time of the cyanobacteria, 3.9 billion years ago, because it goes back even further, to now, you know what the doubling time of complexity is measured by functional base pairs in DNA?
A trillion years? I don't know.
No. It's only a couple 100 million years.
Okay.
And so if you go back and you ask the question, all right, so when did life get started? When was the first simplest, a few base pairs kind of self-replicating creature? How far back you have to go with that sort of doubling complexity evolution timescale? Take a guess.
I don't know.
All right, that's a fine answer. It's 10 billion years. 10 billion years to have the development of the complexity as we measure, and that doesn't even count the time that it takes for the autocatalytic mechanisms to evolve to create the DNA and RNA and DNA that are the alphabet and the language. 10 billion years is twice the age, more than twice the age of the Earth. And,
Sure.
And since there were oceans on the Earth, it's close to 3 times. So there are people that would say, well, you know what, Kevin, there just hasn't been long enough on the Earth since we had favorable biological, an ocean, for example, enough energy to keep autocatalytic things going with coal life. There hasn't been enough time, and so it started somewhere else. And that's not a crazy idea. In fact, was it Watson or Crick, one of the two from the discoverers of DNA, argued that the same thing. He said, panspermia must have been a critical ingredient of life. Okay.
So
we digress. We're talking about breakthrough.
I know. Maybe we should do a whole episode on that. But
yeah, well,
I talked to a guy a couple days ago. He was convinced that there's reptiles on Mars, and they came to Earth.
No, wait. Okay, so that's not what I'm saying.
I know.
But I think.
But it's an interesting.
All of these are questions, right, that are wrapped up idea that, well, is life really just accidental, or are we on the verge of being able to turn it into a science? The point of all of this, I think Milner's point ultimately is, look at world, the Fermi Paradox. Okay, Fermi Paradox means, gee, the universe isn't so big, the distances aren't so large certainly between exoplanets now. Why have we seen no evidence of life? And we can turn that into a scientific question. We can build telescopes now, and that'll be a subject of another talk, I think, where we can learn a lot about what we could learn from a nanoprobe, from if we get lucky, from large optical telescopes that are designed for that. So we could start doing a census of our corner of the galaxy. Right? And by the way, we should talk about Proxima B sometime, because in my opinion, that's one of the most exciting discoveries to happen in the last decade. Well, okay, along with the discovery of gravitational waves, but it's a big deal. It's a big deal that the first time we ever really looked carefully at an M-dwarf star, we found a planet that could have water on it. And
sure,
in my opinion, that's almost as exciting as how 20 to 30 years ago we found an exoplanet around another star. I grew up being taught that, planets are rare and wondrous things, and it'll be unlikely that we'll ever see an exoplanet around another star, and that was just wrong. We aren't special. We aren't accidental. Anyway, okay.
Yeah. All right, I have one more question before I do. I want to show you one thing that Connor sent. It's just a joke based on what we were talking about previously.
Oh, yes. Good work, Connor. We need to fund reconnaissance missions, discover their intentions, support Starshot, support Earth. We could get into trouble though with that.
I know. I'm in
trouble. The militarization of space is not something that we support.
Of course not. But it's interesting to think about. With a big unfortunately, that's a lot of times how things are funded, especially when they cost tens of millions or hundreds or billions of dollars.
Well,
so I would hope that we can do it another way.
Okay, but all right, now I have to say something in response to that, which is the world's largest telescopes have always been supported by foundations and private individuals. So some of the most innovative, futuristic visions of what humankind can do have come from individuals, not from government agencies. Government agencies, unfortunately, don't have the attention span to do a lot of what we want to do. And I think that's really part of the beauty of what Yuri Milner is proposing, which is he's an individual of means, and he can establish something that has a longer attention span than the Democratic or the Republican Party or the military wishes. We went through that, right? When we went to the moon. So what?
Right.
We went to the moon. Our attention span was not sufficient to keep NASA directed towards the bigger questions that were associated with that. And
Sure.
that's why it's so important that people like Milner exist and are willing to push parts of our society in that direction. They're existentially important.
Yeah, completely agree. All right, one last question, and then we'll sign off. So I just have a question about traveling through space at those speeds, and I guess just space time in general. So
This is a relativity question, or is this a question
Yeah.
about survival through space at that speed?
I feel good about the survival, because I mean, there's, I guess, space dust, but it doesn't seem like space dust is that
Well,
big of a problem.
it could be. I mean, that's something that is one of the. There's a list of, like, if you go to the Breakthrough Starshot web pages, there's a resource page that lists all of the hard problems that have to. And there's like 19 or 20 problems, and one of them is at 20% of the speed of light, even a few atoms are going to degrade the surface of the star chip. So the important microelectronics have to be oriented. So if the star chip is like a postage stamp, it has to be oriented edgewise, and it has to have some amount of shielding. But all right, so that's not your question.
Yeah, I guess the question is could you, I mean, I've heard it explained 100 times, but it's such an interesting concept. Just traveling, the faster you travel through space-time, it slows down for you.
Yeah, so if we put an ant on the nanocraft, right, there would be the ant at, let's say, at 20% of the speed of light would feel, what is it like, instead of taking, so from our point of view, the nanocraft takes like 20 years
Right.
to get to Alpha Centauri. From the ant's point of view, the ant, if it was born when we put it on the nanocraft, okay, now you're making, I can't do these numbers in my head, but the ant would only be about 14 years old. But ants can't live to be 14 years old anyway. So, but you get the idea. Yes, the ant would experience would feel like things were faster.
Took less.
Yeah.
And then just a follow up to that. So do planets that live closer to the center of their to their galaxy experience space-time differently because they're moving faster?
It's a tiny
versus
tiny effect. Tiny effect.
Okay.
So the velocities
significant.
aren't large enough that it would make much of a difference.
All right.
But if you want to compute it, the important number is 1 over the square root of 1 minus v squared over the speed of light squared. So take the velocity, 1 over 1 minus v squared over c squared. The square root of that is the factor by which their clocks are slowed down compared to our clocks as they move. Yeah, that's another interesting question. But we've even done experiments where we put atomic clocks on jet airplanes.
On high-speed planes, right? Yeah.
Yeah, and you go up and fly around and come back down again, and yeah, it works. Einstein's special relativity is one of the pillars of science. We're not gonna get rid of it, and that's part of the problem with some of these warp drive ideas. We kind of have to stretch the bounds of relativity to make those work.
Right.
So, did we make it?
I think we made it. Okay. I think we answered most of the questions.
Yeah, we did, and hopefully you out there in the audience, we didn't scare you away. Come back and join us every week as we have a conversation about the cosmic news of the week, and we address the question: are you special, and why being not special is a good thing. Thanks for listening and watching, and come back in a week.
Right? All right. Yeah. Thanks, Jeff. we will see everybody next week. Thank you.
Okay. Thanks.
Uh,